So as we started equilibrium, we said that the rate of forward and reverse reactions or of those opposing processes are equal, but the amount of each thing may not be equal. So the question would be, how can we know how much of each thing we have? It is determined by the energy, it is determined by the organization and the disorder. But why do we have a certain amount? There is an equation that we often refer to as the equilibrium constant or the equilibrium constant expression that's based upon a lab observation called the law of mass action. What was found out for all of these different systems at equilibrium at all of these different temperatures, that if we made a ratio of products to reactants in a certain way, that equilibrium reaction at that temperature always has the same ratio. So the mathematical ratio is called the equilibrium expression. So we have a general equation here that A and B make C and D. The small a, B, C, and D would be the coefficients that go with that. So when we write an equilibrium constant or an equilibrium constant expression, we are putting products on the top and reactants on the bottom. So that our numerator is C and D, our denominator is A and B. It was found that if you just did that, that ratio wasn't always the same. It depended on how much you started and ended with. But if you look at the balanced equation and raise the amount of each of those things to their balanced coefficient, so C to the C power, D to the D power, etc., then that value was truly a constant. That's the law of mass action. And we can represent this mathematically. We do it in two main ways. If you continue on in college or chemistry in college, you'll see how this can even be extended in some different applications. But for the straightforward application of it, we either think of it in terms of concentration, and we call that constant a K, equilibrium constant, in terms of C, the concentration. When we do that, we put the concentration of products over reactants, our coefficients as exponents, and we use square brackets. And those square brackets indicate that we're talking about the concentration in terms of molarity. So we don't use moles or grams here, it has to be molarity. If we're talking about a gaseous system, sometimes it's easier to measure the pressures. So when we do that, we would be thinking about the K in terms of pressures. So we would do the pressure of C to the C power, the pressure of D to its exponent over A and B. This one, we use that capital P and we don't use square brackets. Square brackets means concentration in terms of molarity. When we get to the point where we're solving for these things mathematically, we'll notice whether it's a given value or whether it's what we're solving for, that K does not have a unit. It's molarity over molarity or atmospheres over atmospheres, or those things tend to cancel out. Whether they're canceling perfectly or not, we ignore those. An important piece is this is often the first step in a free response problem where you're looking at an equilibrium system. So writing these correctly and using either the square brackets or the letter P is usually a difference in terms of whether you're going to earn the points or not. So pay attention to the values that you're given, pay attention to the units that we're looking at, and whether they're asking for KP or KC. When we're looking at that, a couple things are important. Whether we're looking at a molarity or a pressure, a pure solid does not have either one of those. They are pure through and through. They don't have a concentration. Pure liquids like water. Well, how many moles per liter do we have of water? That doesn't have a molarity value in the traditional sense. So they do not appear in the expression at all. If we were writing the expression, we would either leave a blank there or we could put the number 1 as a placeholder, whether it's in the numerator or the denominator. And there's some examples with that. KC and KP are not exactly the same because of the way that they're measured, because of differences in terms of how the concentration can impact the pressure. There is a conversion between them. You should be aware of it, but this is not something that would be tested on a quiz or on a test or on the AP exam. But it's all based upon whether we are consuming gas or producing gas throughout the reaction, which is why the delta N, the change in number of moles of gas, is important. But really more important than that is understanding what K means. On the top on our numerator is the products. On the bottom, on the denominator, is our reactants. When our fraction is a value larger than 1, that means the top number is bigger than the bottom number, that at equilibrium, we have more products than reactants, either in terms of molarity or pressure. When K is less than 1, it's because our bottom is a big number, the top is a small number. In that case, we have more reactants, or this reaction, we could say, does not very much go to completion or lies to the left. So we're going to look at that in terms of some graphs, some equations, and some particulate diagrams here with some simple reactions. So here we have something similar to what we saw in the last video, hydrogen and bromine making hydrogen bromide. In this case, when we see the amounts, they'll say these are our equilibrium amounts. We have a whole bunch, relatively speaking, of the HBr. That's the top number. We have very little H2. We have very little Br2. So both the concentration of those, and since this is square brackets, we would think of this as a Kc, but also the pressures exerted by those would be lower. So when we think about that, we'd have a big number on top, and we could even count 1, 2, 3, 4, 5, 6, 7, 8, 9. If I put 9 squared on top, that would be 81. Well, times 1, that K comes out to 81, a value larger than 1 or a large K value. As that reaction occurred, we may have started out with a lot of hydrogen and bromine, but those amounts decreased over time. The amount of product, the hydrogen bromide, we maybe put none of that in the container, but we started to make more and more and more of it until eventually it flattened off here till we had that constant amount of products, constant amount of reactants. And a graph is a great way to show which thing is favored at equilibrium or which thing we have more of, or to connect to the value of our K. This over here, my second example, is nitrogen and oxygen making nitrogen monoxide. So when we look at the picture there, we can count up our blues. 1, 2, 3, 4, 5, 6 right there. 1, 2, 3, 4 right there. Our NO2s, 1, 2. We can do the math on this, but we would want to know not just the number of particles, but the exact molarities. But even counting particles, it still works. 2 squared is 4 times 6, or excuse me, divided by 6 over 4. 4 over 24 is 1/6. It is a number that is less than 1. Once again, we would be using molarities. These are gases, so we could do Kp in terms of pressures if they use the letter P instead of our square brackets. But we would have a number less than 1, and therefore that means even as this reaction occurs, we do make products, but we have more reactants than our products. So our reactants decrease as the reaction proceeds, our products are made, but we get to an equilibrium when we still have more reactants than products. The reaction, and some different terms for this, in this case, the equilibrium lies to the left. I have more of my reactant chemicals than my product. This equilibrium lies to the right. We can also, when thinking about stoichiometry, this reaction goes fairly far to completion, meaning it almost turns all of our reactants into products. This one does not go very far to completion. We still have mostly reactants when we are at equilibrium. So those are some different ways to talk about a big or a small K, meaning a lot or few reactants and products at equilibrium, whether it's a picture, a graph, or one of those phrases. Throughout this unit, the practice problems are on a separate document with their work and answers, and there's videos for them. So really good to get some practice writing your equilibrium expressions.